Let's say that you're working on a data set that you've seen for the very first time. You have a bunch of variables and you want to see whether the cause effect relationship exists between any of those variables. What are some of the things that you can do to explore this data set and see what relationships exist? In this lecture, using a dataset that's freely available in BigQuery, we'll see if we can predict the demand for taxi cabs in New York City. In this first lecture, we'll set up the dataset so that we can perform machine learning on it. This lecture will contain a lot of cleaning up and setting up the data the way we want it to be. This example is part of Google's Code Lab, and the code for this can be downloaded from the Training Data Analyst repository under CPB 100 Lab 4A, and the file is a Python notebook named Demand Forecast. This file should be available to you in the source code that you uploaded into Data Lab, which has all the TensorFlow examples. This code under the Learning TensorFlow folder has only the code snippets. It doesn't have the corresponding explanations because the explanations is what I am going to be giving you. The original file has a ton of very well written explanations using Markdown. If you want to see those, I would suggest look on GitHub or download that file. Open up the file and you're ready to start. The first step, clear all cells so that previous execution results are not visible. They tend to be distracting when you're actually executing it yourself. This is a long and pretty involved example and it uses a whole range of libraries. We use the BigQuery library to read input data from BigQuery, pandas for setting up the dataset in tabular form, NumPy for numerical computations, and shutil to perform some files and directory manipulation. Before we start reading data in, it's always helpful to check out the schema of the table that we are going to query. This is a table in a public dataset that's freely available to us, and it has a whole lot of interesting data on trips passengers have taken in cabs. For every trip, you have information available such as the pickup time, the drop off time, where exactly they were picked up, the lat long coordinates, the trip distance, the fare that the passenger finally paid, and also how long cabs were idling just before this trip. One of the columns that we'll query is the day of year. This assigns an integer identifier to each day of the year. 1st of January is 1, 2nd of January is 2, and so on. You can examine this result. The extract function seems to work just fine. Let's move on to the actual query that we want to set up. If you observe the table name for this taxicab data, you'll notice that the suffix of that table is a year. 2015 means the data is for the year 2015, 2014 means the data is for the year 2014, and so on. We'll set this query up so that it's parameterized on the year, which means you can pass in the year for which you want the data as an input variable. We want to predict the demand for taxi cabs in New York on any day. Now, let's set up the number of trips as being a representative of the demand for taxi cabs. There are, of course, other values that can serve equally well, such as the total amount spent on taxis, but this example uses number of trips for simplicity. For every day of the year in any year, find the total number of trips made by taxi cabs. In order to execute this query, you need to specify the date input variable, the date for which you want this data. In this example, we first get the data for the year 2015. This is passed in as a string parameter and appended to the end of the name of the table. Execute the query and pass the JSON that you just set up as a part of the query params. BigQuery provides very convenient pandas integration. You can convert results from a BigQuery table to a pandas data frame by simply calling the toDataFrame method. We then just sample the results in this data frame to get an idea of what it looks like. And there you see it, a data frame with the day number and the corresponding number of trips. This is for the entire year 2015. There are many ways to get a baseline. One way is to simply calculate the average number of trips for all days in a year and find the root mean square error of this average. Root mean square error is the same as the MSE that we've seen before, except that we find the square root of the MSE. This baseline gives us an RMSE of 10,000. Remember, lower values of RMSE are better. Let's see if our TensorFlow models beat this when we actually implement them. This benchmark or our baseline basically means that if you were to predict that there will be 55,000 trips every day, we'll be off by 10,000 trips. This average prediction of 55,000 can be an overestimate of 10,000 trips or an underestimate of 10,000 trips. Let's say that you have a theory that you want to confirm or disprove using this data. You believe that the demand patterns for taxi cabs depend on the weather in some way. Let's test if your hypothesis is correct. This we can do by using the table which has our weather information. We've used this table before in earlier examples. This is the Public Geological Survey dataset, and we want to query the stations table to know which is the weather station where we can get information on New York weather. This is the where clause that will help us find the station. State is equal to New York, name like LaGuardia, and so on. You can see that the station with ID 725030 will give us New York weather. We'll query the table which has the weather information to get various details of the weather for each day of the year in the year 2015. The column that's common between this weather data and the number of trips data that we got earlier is going to be the day of the year. So extract the day of the year information from this table as well. In addition to the weather, say you also believe that taxicab demand differs by day of the week. Say you believe demand will be high on Saturday when people go out to party. Day of week will give you information as to what day of the week it is. Starts off with Sunday being 1 and Saturday being 7. And here is the weather data. We get the minimum temperature on that day, maximum temperature, and a number representing how much it rained that day, the precipitation. The temperature data is in Fahrenheit and the precipitation data is in inches. Notice that we get this information for the weather in New York. We use the identifier for the station, which gives us New York City's weather. We once again parameterize this table as well by year, so we can pass in the year as an input variable. Execute this query by passing in the year as 2015. That's the year for which we have taxicab data. Now we have weather data and day of week information for this year as well. Execute this query and sample 5 records in the result to see what the data looks like. The next step makes one data frame of all the information that we have. We have the weather data and the number of trips for every day of the year 2015. We can perform a join operation where the join column in traditional SQL terms is the day of the year. In pandas, this is super straightforward. Simply use the PD merge method. If you examine the result, you'll see the day number column that is common to both data frames. The next 4 columns form the data from the weather table, and the column after that is the number of trips from the taxi table. Before you go ahead and start setting up a machine learning model, you might want to quickly explore the data to see if any relationships exist. There are a bunch of tools that you can use to do that. Since we are already using pandas, we can use the plot function in pandas to help us see visual representations of this data. When we examine data visually, you might find some relationships exist. Something might jump out at you. In this step, we'll see whether a relationship exists between the number of trips on a particular day and the maximum temperature on that day. We'll plot a scatter plot to visualize this. This scatter plot doesn't seem to hold much information for us. There is no obvious clustering around certain temperatures or no obvious linear or some other kind of relationship between these two variables. Let's explore another variable that might be more promising, the day of week and the number of trips. What you've seen anecdotally is that you can never find a cab on Saturday. Let's see if that translates to more trips for the weekends. And you'll immediately notice that this visualization has much more information and is much more interesting. Day of the week is, of course, categorical data. It has discrete values. Days go from 1 through 7. Days 6 and 7, that is Friday and Saturday, have a significantly larger number of trips as compared with other days. You can postulate a number of theories for why this might be the case. For example, if New York, which is a tourist destination, has a number of tourists pouring in on the weekends and looking for cabs, the demand would be higher. If you look at the days in the middle of the week, such as Tuesday and Wednesday, the demand is significantly lower. If you were to use this data to recommend to taxi drivers what days they should be taking off, you would recommend Tuesday and Wednesday. Now, it might be that you still believe that the maximum temperature has some effect on the demand for taxi cabs. But this day of week effect is so strong that it might be obscuring the relationship with the maximum temperature. A way to test your hypothesis would be to examine the relationship between the number of taxi trips and the maximum temperature for the same day of the week across the entire year. That's what we're trying to do here. We are trying to eliminate the effect of the day of the week to see whether maximum temperature now has any effect on the number of taxi trips. Let's plot the number of trips for every Saturday against the maximum temperature on that day. Again, if you take a look at the plot, there's not much information there. One thing should strike you though, that the number of data points are far fewer than we saw in the other graphs. There's just not enough information there. Let's say instead of just working on the year 2015, we were to include a few more years of data, we might find that a pattern exists. On that note, this example adds one more year of data to our dataset. Set up the query parameters as we did before. This time specify the year as 2014. And here is why having the right parameterized query is so important. By simply setting up the same query with different year values, you're able to quickly get data from different years. Run the query for getting taxicab trip data as well as the weather data for the year 2014. Merge the data together, performing a join on the day number into a single data frame as before. This is data 2014. Execute the query and sample the data. It looks fine. It's kind of annoying working with a data frame which has data from 2015 and another which has data from 2014. This is all the same data. We can simply bring these two data sets together using pd.concat. The combined result is stored in the data frame data2. The data2.describe command will give you statistics on all the columns of data that's stored within this data frame. These are the standard statistics that you might need to know in order to understand and get a feel for this data. For every column value, there is the count, mean, standard deviation, min, max, and all the quartiles. Across the 2 years, 2014 and 2015, we have a total of 546 records. For these 546 records for every column, here are other statistics. The day numbers range from a minimum of 1 to a maximum of 365. That makes sense. The number of trips per day also vary pretty significantly. It goes from a low of around 13,000 trips to a high of around 81,000 trips on a single day. Let's go back and see if adding this additional data set for the number of trips in 2014 allows us to view some pattern in the effect that maximum temperature has on the number of trips per day after eliminating the effect of the day of week. This is for Saturday. The resultant plot is a lot more interesting. There is more clustering around the higher temperatures, but again, there is still insufficient data. You might have to add a couple of more years to see whether a real pattern emerges. We believe that some relationship exists between our predictor variables, that is, the day of week, and the weather on a particular day, the number of trips that passengers take on New York taxicabs. Let's run a TensorFlow regression model in order to see what this relationship is. So, what would you do if you're working on an unfamiliar data set? You need to understand the data and you want to explore what relationships exist. You'll typically set up the data set in a way that makes sense to you, and you'll perform a few exploratory visualizations in order to see what kind of pattern emerges. If visualizations give you an idea of the patterns that exist, that's great. You have some kind of objective in mind when you set out with your machine learning models. Just a caveat though, patterns may not always jump out at you when you're visualizing the data. Sometimes you believe patterns exist, they might only be extracted with machine learning algorithms.